Beep, 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 beep. 20 minutes. Look at you. Like I made your brains go into overdrive or something. Let's have a look at this now. Actually, I'm going to start my... No, I have a stopwatch running on the computer. I want to see how long it takes. A small mass is suspended from 1.8. What's the amplitude? 10 centimeters, isn't it?
Yeah.
Okay, well that's easy peasy. You keep it cool, Zach.
Yeah. Wrong.
Okay, just minus 0 then. Oh, that's minus 0. Well, that seems very easy.
Minus a 0 would still be 0.0.
Zach. Right. What is the frequency? Oh, show that the frequency is 0.37. So the frequency is 1 over t, which is 1 over 2 pi root g over L, which is 1 over 2 pi root 9.81 over 1.8. Is that 0.37?
Yes.
3. What is the maximum acceleration and when does it occur? So the maximum acceleration occurs at the low point, at the equilibrium. And the acceleration would be equal to... No, that's wrong. That's wrong. It's not at equilibrium. The maximum acceleration occurs at the amplitudes, at the ends, at the endpoints. And it will equal omega squared x, where the x is a. So that's equal to 2 pi over t squared a, which is also the same as 2 pi f squared a, which is 2 times 3.1415 times 0.37 squared times 0.1, which is
0.540. Which have the second square?
0.545.
545.
Yeah, this one, if you go with yours,
Yeah, but it's not exactly 0.37. 371 is better. You get 545, is it?
Yeah.
Okay, thank you.
that's good. But
What's the maximum velocity and when does that occur? That's at
yeah.
equilibrium. And you can use the formula V equals omega root a squared minus x squared. And when it's a maximum is when the x is 0, isn't it? Which is just omega a, which is omega is 2 pi fa again. So that is 0.371 times 2 times pi times 0.1.
So the formula V equals a omega cos times omega t
Yeah,
gives you the velocity for wave.
it does. At any time t of your choosing.
So 5.3, what velocity?
Yeah, that's the idea, yeah. Right, what's the answer here?
0.233.
Okay. I've already done part A. B. If the point 3... Sketch a graph of the kinetic energy against displacement. Include the values. Okay, well first I'll do the sketch. Then we'll add in the value, okay? So, displacement is x in meters, and the y-axis is kinetic energy, or in joules. At the beginning, its x is 0.1, and it will have no kinetic energy, right? And then the kinetic energy will increase, reaching a maximum here, and then it will decrease back here. And we need to mark in this value here. This is the maximum kinetic energy, which is a half m v squared, and we got the maximum v, which is 0.233 squared. So that's a small number. What's that?
8.143. times 10 to the power negative 3.
Joules.
Right, so what I'll do, I'll just,
8.1.
143.
hang on. Where's my pen? Where's my, oh, hang on. What the heck happened here? There we go, sorry. I'll just remove this for a second and just change it to millijoules, make my life easier. And what is it, 8.14?
143.
So I'll just call this 8.14 millijoules.
So what is an acceptable range for this graph?
What I have is
One-
fine.
one-
Yeah.
one-
It's only a sketch, isn't it? C. So now, can I scroll down?
Yeah.
So now what you have is your pendulum. What was the length of it? 1.8? And the mass was 0.3
3.
kilograms. And how many more?
5.
Okay, what's the length of the first one?
1 meter.
Okay,
1.4.
okay,
1.8.
okay.
2.2. 2.6. So it's 0.4 increase.
2.6.
2.2. 1.8. 1.4. 1.
And they're all 0.1, aren't they?
0.01.
0.01.
Yeah.
They're all 10 grams.
Yeah.
All 0.01 kilograms. Okay. So what's going to happen is this is going to move with simple harmonic motion. And it's on a string here, which means the vibration will move down the string and cause these to move as well. Right? Now the reason for that is kind of obvious. Like if I just start vibrating this table, you three can feel the frequency, and what's going to happen is my pendulum is going to make the other one start to move. Now some of them will move with a small amplitude and some of them will move with a big amplitude. The ones that will move with the biggest amplitude are the ones that will have the same frequency as the original. So they've already told us that the frequency is 0.37. Okay? That was given earlier, wasn't it? So the question is, which one of these can have what's called, I think it's called a sympathetic frequency, a same frequency. No, why is that called sympathetic? That sounds like a mumbo-jumbo word. Okay, so if you look at the formula for frequency, guys, look. The formula for frequency is 1 over T. So to have the same frequency means to have the same time. But the formula for 1 over T is 1 over 2 pi root L over G. Now 2 pi and G are constants. So really, for a pendulum to have the same frequency would mean that you would have the same length. So let's be very clear about our answer here. We would have the 1.8 meter 0.01 kilogram will have the most amplitude in its swing. Okay? Then the 2.2 meters and the 1.4 meters would be the second most amplitude, I would say. And then the 2.6 meters and the 1 meter would have the least amplitude. So when you picture all of these swinging, this one will swing the most. Then these two will swing not as much. And then these will swing a little bit. Okay?
What is frequency over mass?
Yeah, this is what we discovered when we were doing the forced. Do you remember that forced harmonic oscillator? The only thing that matters is matching the frequency. The amplitude, the mass, the size, it doesn't affect how much harmonic amplitudes you have in the neighbouring system. You know, it's quite. This phenomenon is called resonance.
Quantum bridges.
Yes, exactly right. I think we discussed the bridge example, the Millennium Bridge. Okay, are we okay with that? I wonder, did anyone get that? Is it 3 marks?
Yeah.
See, I kind of have a feeling it's 3 marks because it might be 1, 2, 3 like this.
Oh.
Maybe, I don't know.
Can
Because
you
didn't they? What did they say?
describe or explain what you see?
Describe what you'd expect to see describe what you expect to see. So to me, that sounds like you need to describe what happens to all the pendulums.
Does that mean that you actually have to do the calculation or just say?
No, just like what I did, it's apparent that same length would equate to same frequency.
And the pendulums will begin to swing 1 mark.
Yeah,
The 1.8 meter pendulum will swing with the greatest amplitude.
yeah,
It will initially be pi over 2 behind the original pendulum. The original pendulum will lose amplitude. The other pendulums will remain at smaller amplitudes. After some time, it may begin to leave the original pendulum. and lose
Wow.
amplitude as it transfers energy back to it.
wow, unfair, dude, unfair. So the problem I have with the 3rd mark is you only get that if you've done this experiment. But that kind of sucks because this isn't on their list of experiments the students need to know. It just really sucks. I did this experiment in
Yeah, how
second.
would you know
In,
it's pi over 2?
exactly, and how would you know about the transfer
Mm.
unless you do it? I did this experiment in high school, because it's a cheap, simple experiment to do. I'm disappointed because to me it would sound like it's impossible for students to get the last mark unless they've done this
Obvious-
experiment,
a
which is
possible
not on the syllabus list.
1, 2, 3, 4, 5. Possible 6 marks.
Oh, good. Okay, so they give you 6
6
targets. You have to hit. Okay, well, continue. What's some more then?
I read all of them.
Oh, right. Can you read them again? First mark is.
Other pendulums will begin to swing.
Okay, stop. Pause there. Will I get that mark? Yes, because in my answer I acknowledge all of them are swinging, so I have that mark. Okay, continue, Zach.
The 1.8 meter pendulum will swing with the greatest amplitude.
Good. So I've gotten the second mark of 3.
Then it's the 3rd mark is it will initially be pi over 2.
Yeah, so we won't get that. Okay.
The original pendulum will lose amplitude.
Didn't say anything about that.
The other pendulums will remain at smaller amplitudes.
Oh, good. Right. So there's my last mark because I said the other 2 are less. Okay, fine. So I got my full marks.
I don't understand this one. After some time, it may begin to lead the original pendulum and lose amplitude as it transfers energy back to it.
Yeah, what's happening, if I remember, is that there's kind of an interplay where the original pendulum kind of slows down and the other ones start to excite more, and then they reverse roles again.
So they lead the
Yeah, so originally the first pendulum is leading the swinging, and the other ones then follow in suit, and it slows down, and the other ones are going quite significantly, and then it reverses roles again. So, yeah. Okay, well, that's fine. Right, D, finally. The original pendulum is now interrupted, if you will. What would be the ratio of the time period? Oh, okay, fine. Baby stuff, right. So they want to know what's the ratio of time 1 to time 2, where time 1 is a 1.8 and time 2 is a 0.9 length pendulum. So that's 2 pi root L over G, L1, over 2 pi root L2 over G. Everything cancels except for the L's. So that would be root 1.8 over 0.9, which is 1.4141. So the ratio is 1.41 to 1. This is your longer pendulum to your shorter pendulum. Right? Yeah? They want the ratio of the 2 times, that's all. And lastly, what would the time be for the 0.9? So the time would be 2 pi root L over G, 2 pi root 0.9 over 9.81. What's that? You have that, Gina?
2 pi 0.9. It's 1.90.
1.90?
Yes.
Now, how long did it take me to do that?
Wouldn't you have to?
15 minutes. Oh, I have loads of time left.
So it's not 0.9
No.
for the whole time.
That's it.
It's only 0.9 for half the moment.
Oh, I got too cocky and read this too quickly. Sorry, thank you.
So you have to.
Yeah, I have to. I'm not finished. So, what was the original time?
You have to work it out.
Okay.
But so you can just time.
Yeah, no, okay. Okay, what you get? 2.69 seconds. Right, so it tries to swing forward and back, but what happens? It's interrupted when
At half. At equilibrium.
at equilibrium. So as soon as it gets to here, they grab it
Somehow in no time.
and
Half the length.
it now continues to swing up
Yeah.
and back. So the total time will be a quarter plus 3/4.
Oh, yeah, it's not on.
Yeah,
Right now it's
they did half. Those fiends.
Well, maybe it implies that at equilibrium they drop it down again.
No, I think they screwed it up. Because, they said you release it,
Yeah.
and then as soon as it gets to equilibrium, which is not half the journey, it's only a quarter of the journey. So I'm quite happy that we have it right here with the quarter, 3/4. Unless I'm misreading something. The original pendulum is now arranged so that it passes through equilibrium. The thread is interrupted at a distance of 0.9 from the point of suspension.
Yeah, your assumption is correct that it's a quarter and 3/4.
I'm just afraid that.
This is such a badly worded.
Yeah, actually when I looked at it, I thought it was like here.
Who wrote this?
Yeah.
Go to jail.
He's just messing with them.
Like, I didn't, when I first read it, the thread is interrupted at a distance of 0.9. I had no idea what he wanted.
Yeah, I thought that was like from an equilibrium, which didn't make sense because the equilibrium is amplitude only 0.1. Yeah, D here is badly written. We're actually assuming that it's grabbed at equilibrium only because it says it passes through equilibrium.
Maybe they assume that it was already like doing the thing, like they just got it instead of releasing and
Yeah.
did it. So
Oh, I
it's,
think it's too high.
Oh, I think Diego's right. I think Diego's right.
What do you mean?
No, the way Diego said it. I think when they said it's arranged. Can you listen? Listen, I'm giving you some English here. When they said it's now arranged to pass through equilibrium, I don't think that's telling us that they grabbed the string at the equilibrium point. I think, as Diego said, what they're trying to say is it's swinging, and you imagine it begins when it's in equilibrium. Like that's the starting point now, rather than out here, because it's swinging. But then that leads to the next question, Diego. How do we know where it's grabbed? Do we just assume you grab it when it's at the end? Then that's the same problem as before. It's
No,
1/4.
when it passes through,
Yeah.
you take it and then whoop, 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 whoop. You know, because you can have. a
Yeah, but
string-
what do you take as the starting point?
Here they say from the point of suspension.
You can get the equilibrium point as point of.
But now it says as it passes through equilibrium.
Where does it say that?
As it passes
It
through.
says as it passes through equilibrium.
The point of suspension is here. Is it?
So it's the length of the suspending wire is halved as it passes through equilibrium.
Okay, and I think we also need to assume it starts from equilibrium.
Original pendulum.
Yeah, because it's arranged so that it passes through equilibrium. The thread is interrupted from the point of suspension.
But that as makes.
The as is not clear. The as doesn't tell me if we should A, assume it starts from equilibrium, B, that we grab it when it's at equilibrium, or C, both. It starts from equilibrium and then we grab it when it's next at equilibrium. It has to be the third option to match the marking scheme. That it starts from equilibrium and we grab it the next time it goes through equilibrium. That's the only explanation that matches the marking scheme. Of course, that's no good for you in the exam because you don't have access to the marking scheme.
So you just have to guess.
I'm afraid so. This is the hard facts of life, that sometimes whoever writes an exam question is not clear with their English.
But then if it happens that you put 3/4 and they put it wrong, can you like? 'Cause you
Oh, I
have-
put this in my report when I send the exams on, you know, question not clear or whatever. But don't think that means anything because they usually don't listen to me. So I would say that if I write some criticism of the exam, I don't know if it's their pride or what, but there's only a 25% chance that they'll acknowledge my criticism as valid, you know. But look, I'm only telling you this not to feel bad, but just, you know, that's just the hard facts of life, you know. Yeah. Now, look, the thing is, I will be with you in the exam to answer any kind of questions. Now, I can't answer physics questions, but this would be a good example of a question I could clarify for you in the exam, you know, because I feel like this isn't a problem with physics, this is a problem with how the question was written. So, this is why I'm in the exam with you to answer, you know, these types of things. You're like, oh, teacher, does this mean A or B, you know? And if I feel like, oh, the question isn't about physics, but something, you know, about how it was written, I could help you with that.
We
You know?
write like if we to assume it's
You do
this.
not have the time to be looking at different scenarios. Now, if you did,
Yeah.
that would be wonderful.
Would you still mark like the correct?
Oh yes, I would. In a situation where I felt like the question was unclear,
Yeah.
and the student heroically went to the trouble to look at both situations, then I would mark their correct one. I would reward the heroic effort. But like I said, the time is tight, you know. Okay, that question at the end wasn't great. But apart from that, I thought the rest of it was manageable.
Yeah.
Yeah. Now, we could look at other section B questions. For example, we've got a mechanics one that doesn't look too hard. And we've got a... Okay, what other type of section B question do you want to do? We could do another simple harmonic motion one if you could find it. We could do an electricity one, whatever you want. Why don't you open up Moodle and have a look at the other versions of the exam? You guys tell me which one looks tricky. Yeah, tricky one.